Good evening all. Let's get started with today's session. So before going to discuss on today's session, there was a query regarding the last week's session. So essentially the question was when there was a question in assignment 3 where the participant was not able to get the same answer using the iterative method and a direct method. So let me just share my screen. I hope my screen is visible. So this was the code that was shared to me. So here the grid points are 5 and the delta y for each grid point is 1, dy is essentially 1, and the tolerance is specified as 10 to minus 10. So these are my boundary conditions, both are Dirichlet conditions. So if you go into the problem over here, so the AP terms are updated as twice, and A west and E east are 1 each respectively, and your B term is essentially 0. Now for the source term, where since the source term is varying as a function of x, so the discretization is as 6 times this particular value I plus to dy is your xp into delta y square. Now at the boundaries your AP term is essentially changing, and on the west boundary your A west AW is 0, and on the east boundary AE is 0, so this is also fine. So now when the implementation comes to a Gauss-Seidel method, the notation we are following in this particular updation of coefficients is for an ith cell, the matrix AE has the coefficient of AE on the ith cell is equals to the AE of I. So this particular term over here should be replaced with AE, and here AI. I think this solves the problem. So if you run this code, so the results are matching with the values obtained from the direct method. With this, I think we can get started with our session. So we'll get started with this week's lecture. So as you can see here, the first question is essentially the standard film problem, where you have steady state conduction in a constant area of film, so area is essentially not changing, and then the governing equation is given by dx of k times dt dx plus hp by a, where p is your perimeter and a is the cross section area of the film. Tf is the ambient temperature or the fluid temperature, and the boundary conditions are at the base where x equal to 0 you have a T equal to P naught, and on the other tip you have the other end you have an adiabatic tip. You have an adiabatic tip. So the first question essentially asks you to convert the above equation into a non-dimensional form, and then we discretize the equation using FVM. Then you obtain the general form, you obtain the general form of the equation, and then write down all the coefficients AP, A east, A west, and B. And we also try to comment on the non-linearity of the PD as well as the discrete equations. So we have a film. This is a constant area of film. This is x equal to 0. This is x equal to 1, and the governing equation is ddx of k times dt dx plus hp by a tf minus t equal to 0, with the boundary conditions as t at x equal to 0 is an isothermal base T naught, and t at x equal to 1, this is an adiabatic one. So for adiabatic tip we have the boundary condition as dt dx at x equal to 1 equals 0. So this is the Neumann condition. And this is your Dirichlet condition. So the first part of the question asks you to convert the equation into a non-dimensional form, wherein you have theta equals t minus tf by t0 minus tf. So in this particular case we get obtain the value of t as t0 minus tf times theta plus tf. So from this we obtain dt dx equals t0 minus tf into d theta dx. So now if this is equation 1, this is equation 2, and this is equation 3. Now you substitute 3 in 1. What we essentially get is d dx of k times your T0 is essentially your base temperature, and Tf is the fluid or the ambient temperature. Both are being essentially equal to each other. Both are essentially equal to each other. So not equal to each other. Both are essentially a constant that are independent of your that is independent of x. So you can just take that out. T naught minus Tf into d theta dx plus you have hp by a times tf minus t equals 0. If I just since k is also thermal conductivity is also constant, so I can just take it out. So the equation is something like d dx of d theta dx minus hp by ka times t minus tf by t0 minus tf equals to 0. This term over here is essentially the theta that we have defined. So the governing equation in the non-dimensional form is the d dx of d theta dx minus hp by ka into theta equal to 0. In the question it is given that hp by ka, you can take the value of hp by ka as 2. So if I just substitute that back here, so we get d dx of d theta dx minus 2 theta equals to 0. So this is the governing equation that we obtain. So the next step is essentially to use the finite volume method to discretize this on our domain. So our domain, so the discretization can be done in two different ways. So if you see, we have a domain of x equals to 0 to x equals to 1. So the first way of discretizing is we fix the nodal points. So we fix x equal to 0, and then we choose these points, and then we draw the control faces or your control surfaces. So essentially, if I am drawing at exactly half of these nodal points, so these are my control faces. So for the last cell, the face will come outside of the domain, and essentially you will be having only the half control volume. Just take the last cell. So for the last cell, you have the boundary point here. So your one face comes over here. This is the last but one. So n minus 1 cell. This is the nth node, and this is your imaginary surface that comes towards the extending outside the domain. So this is one way of discretizing. The other way of discretizing is instead of starting with the nodal points, you start with your faces. So I choose my faces first. I split my domain into faces, and after fixing my control surfaces or the control faces, then I will fix on my nodal points as the geometric centers of each and every volume. So if this is my volume, I fix this as the cell centroid as my node. So you see the advantage with this is all your control phases will be within the domain. So here the problem is phase is outside the domain. But you got an advantage here. So advantage is, this is actually a disadvantage. The advantage you get over here is you know the exact value of the boundary value, the value of the point at the boundary can be calculated. The boundary value can be determined directly. This is particularly useful when you have Neumann or mixed boundary conditions where the boundary value is an unknown and then you need to determine that. So if you see the second option, in the second case, the advantage is all the phases are within the domain. Obviously the disadvantage is you have if the boundary points need to be approximated separately. They need to be approximated. So this will induce some error in the calculation of the boundary values. So you have to decide which one. So in our particular case, we have Dirichlet on one end and Neumann on the other end. So I'll be going with this approach. So just call this approach 1 and this approach 2. So I am going with approach 2. So in approach 2, if you consider this, so this is my domain. So this is my x equals 0, this is my x equals to 1, and these are my boundary, these are my nodes 0, 1. So this is my I minus 1, I plus 1, so this is my n minus 1 and this is my n. So we will write the equation, we will follow the same procedure as before. So you discretize over a general interior cell and then you take boundary cells separately. So first we will start with an interior cell. For any interior cell you have following. So this is the P, this is a west cell, this is the east cell, this is the phase center small e, and this is on the west phase small w, little w. So if you take our original equation, d dx of d theta dx minus 2 times theta equals to 0. So we integrate over this particular cell. We integrate over this cell. So the integration is from west phase centroid to east phase centroid times dx equals 0. We just do the integration. So the first term is so you have essentially west to east d dx of d theta dx, and then you have west to east 2 theta dx equals to 0. So the first term over here becomes d theta dx evaluated on the east face minus d theta dx evaluated on the west face, and this we are approximating it at the cell centered value. So this I am essentially saying this is equals 2 times theta p. Theta p is the value of the cell of our interest point p, and into delta x equals 0. So for the gradient we will use a linear approximation. So d theta dx on east face is essentially theta east minus theta p by delta x minus theta p minus theta w by delta x minus 2 times theta p delta x equals 0. So if I just group the terms together, so you have for theta e we have a term of 1 over delta x, and for theta west we have 1 over delta x. We don't have any constant terms here, so I'm just writing 0. equals, and for theta p we have 2 over delta x. This is one from the east term, one from the west term, one from the east flux, other from the west flux, and then we also have a term coming from the source, 2 times theta p delta x. So this is essentially my A east, this is my A west, this is my B term, and this over here is my AP term. This is for the interior cells. Now let us see what happens on the west boundary, left boundary. So let's just say left boundary. So for the left boundary, we have an isothermal phase. So if you have seen the equation is given as t at x equal to 0 is t0. So if you calculate theta at x equal to 0, that essentially gives you t0 minus tf by t0 minus tf, that is essentially equals to 1. So I have my boundary value on the west face. This is my cell. So this is my 0 cell, or let's say this is my P cell, and then I have an east cell. On the west I don't have a cell, I just have a west boundary. So this is my east face. So if you try to discretize on this particular domain, so the equation still remains the same. dt dx calculated on the east face minus d theta dx calculated on the west face minus 2 times theta p delta x equals 0. Now on the east face the flux still remains the same, so that is theta e minus theta p by delta x, minus on the west face. Now we don't have a point towards west on the cell centroid, so we will be taking the value on the boundary itself. So we will take a value on the boundary itself. So that essentially gives you theta p minus theta west boundary by, now the domain length is essentially delta x by 2. So we just write delta x by 2 minus 2 times theta p delta x equals 0. So now if we again group the terms together, we have theta east times 1 over delta x plus theta west. We don't have any terms for theta west, but now we have a constant term, 2 times theta wb west boundary by delta x. This is my constant term, equals, now if you take for the terms, group terms for theta p, we have a 1 over delta x from the east flux and 2 over delta x from the west flux. So this essentially becomes 3 over delta x, and then we have 1 from the source term, that is 2 theta p delta x. So this is my A east, this is my A west, this is my B term, and this is my AP term. So this is for the Dirichlet type of boundary condition. Now on the right boundary, now if you see on the right boundary, so you have a Neumann condition. So this is my right boundary where it is given like d theta dx is essentially equals to 0. So this is my P cell, and this is my west cell, this is my west face. So again here the equation remains the same. You calculate d theta dx on the east face minus d theta dx on the west face minus 2 times theta p delta x equals to 0. So on the east face we know that it's an adiabatic tip, so essentially this flux goes to 0. On the west face d theta dx will essentially be theta p minus theta w by delta x minus 2 times theta p delta x equal to 0. Now if we again write the equation, there are no coefficients for the east face, east term, and for the west term we have 1 over delta x. Now we don't have a b term over here, and if you collect the coefficients of theta p, we have 1 over delta x coming from the west flux and 2 theta p times delta x coming from the source term. So this is my A east, this is my A west, this is my B term, and this is my AP term. Now if I write all the equations together, so for I value, and then we'll write A east, A west, AP, and or maybe I'll write AP, and then the last is your B term. So for I equal to 0, that is your left boundary. We have on the left boundary we have A east term 1 over delta x there is no west term, and your AP is essentially 3 over delta x plus 2 theta p delta x, and you have a b term that corresponds to 2 times theta wb by delta x. Now for all the interior cells from 1 to n minus 1, I have an A east of 1 over delta x, AW of 1 over delta x, AP of 2 over delta x plus 2 theta p delta x, and there is no b term. And for the last cell, we don't have an east term. The west term is 1 over delta x, and AP is essentially 1 over delta x plus 2 theta p delta x, and there is no b term. So if you observe, this is a Dirichlet condition, so you have a b term, and this is the Neumann condition where you don't have any source terms that get added over here. So when you have Dirichlet or a boundary condition, you get to add values to both your AP as well as the b terms. But when you have a Neumann condition, the term gets added to only your AP, that is also from the flux. So in this particular question, the problem is essentially like an adiabatic one, so you don't have to deal much. Say suppose you are given a different kind of boundary condition. So this solves the problem of question. So okay, we got the expressions for AP, AW. So we derived the non-dimensional form. We discretized the equation. We got expressions for AP, A east, and AW and B, and the non-linearity of the PDE. Okay, the PDE, if you consider, this k is a constant and this is your right hand term. So as we have discussed previously, how do you say PDE is nonlinear? How do you check for nonlinearity of PDE? Is from the governing equation. So how do we check is essentially, if you have some coefficient, so here we have a second order differential equation, so you have a times uxx plus some b equals 0. We call an equation of this form as nonlinear if the coefficients a, the coefficient a of whichever is preceding the differential equation is a function of my dependent variable or my variable of interest. So essentially, if it is a function of u, so u is the variable that I need to find, so which is an unknown, and my coefficients are also a function of the unknown, then is when you call the PDEs as nonlinear. So in our particular case, these are all constants. So a is essentially a constant, so it's a linear PDE. So the equation, so our particular equation d square theta by dx square minus 2 theta equal to 0 is a linear PDE. Now when it comes to the discretized equation, our equations are of the form AP theta p equals AE theta east plus A west theta west plus p. So this is again linear. So our PDE as well as our discretized equations both are linear in nature, so we don't have to worry much about them. So now let's consider a different kind of boundary condition. Say suppose you are given the flux. So say suppose on the, say you have something like this where this is your P cell, this is your west cell, this is your west face, this is your east face. Now instead of specifying the value of temperature on the east face, you are given the flux on the east face. So this Q double prime is essentially the flux on the east face. So if we write the equation, so previously we have d theta dx on east face minus d theta dx on the west face minus 2 theta p delta x equal to 0. Now if we see Q double prime is given in the direction pointing towards right. Now your x-axis is also pointing towards right, so d theta dx will essentially be positive if it is in the direction of x. So this particular value will be Q double prime. It will be directly equals to Q double prime and minus d theta dx on the west face is theta p minus theta w by delta x minus 2 theta p delta x equals 0. So in this particular case, if you group the terms, you have for theta w you have 1 over delta x, and we have a constant term here which did not appear in the case of, okay, we don't have an east term. this constant term is not appearing in the case of Neumann type of condition where you have an adiabatic tip, and this will essentially equals, if you group the terms for theta p, you have a 1 over delta x and 2 times theta p delta x. So this is the additional term that you will be getting when you have a non-adiabatic tip. So, and then you can solve accordingly if you are given the flux. Let's go to the second question. So the second question is essentially similar to the first one. So the equation is also similar. The only difference is the s term over here is a constant. So previously we have a source term which is a function of temperature, but here source term is a constant term, and then the other difference is in your boundary conditions. So our governing equation is k times d square t dx square plus s equals 0, where both k and s are constants, and we have the boundary conditions as on the left face. So if I just draw a domain like this, so this is my left face, x equal to 0. This is on the right face, x equals to L. So on the left face, if I write minus k times dt dx, this is my heat flux at x equals 0. So this will essentially equals, it is given as H0 into T0 minus Tf, and on the right face x equals to L is HL Tf minus TL. Or maybe it should be the other way. So essentially what we are saying here is minus k times dt dx at x equal to 0 is essentially the heat flux that is at x equal to 0. At x equal to 0, the heat flux is equals to some constant h times some temperature difference. So essentially the boundary conditions are specified in terms of the heat transfer coefficient, or you essentially specify the heat transfer coefficient and the ambient temperature. So H0 and HL are specified at both the boundaries, and your fluid temperature is given. So these are my knowns, and the T0 and TL are the boundary temperatures. These are essentially unknown. So how do I go about solving this? Again, the first step is you take your domain, then you discretize it. Say this is my P cell, east cell, west cell. So maybe for the interior cells it is again quite straightforward, it's the same equation. So if you just take an integration, so you will be getting integral, so this is my west to east, so from west face to east face, ddx of k dt dx, west face to east face equals 0. So if s is a constant, so we can just get this as k times dt dx on the east face minus k times dt dx on the west face plus s times delta x equals to 0. So if we take a linear approximation, so this gives you k over delta x t east minus tp minus k over delta x Tp minus T west plus S times delta x equal to 0. So if you just take group the terms together, for the east coefficient we have k over delta x, for the west coefficient we again have k over delta x, and we have a constant term here S times delta x. If you group the terms for Tp, we have 2k over delta x. So this is my A east, this is my A west, this is my B term, and this is my AP term. So this is fairly straightforward. Now when it comes to the boundary conditions, So if you take on a boundary, so this is my P, this is my west boundary, this is my east cell, this is my east face. So now when we try to apply the same equation, so k times dt dx on the east face minus k times dt dx on the west face plus s times delta x equals 0. So on the east face it is again straightforward, it's k by delta x, and if we take a linear approximation it's t minus tp. Now on the west face we can write it as k over delta x. West boundary, it is given as the temperature is T0, so we take Tp minus T0 by, instead of delta x, now we will have a delta x by 2 plus s times delta x equals to 0. The question is, if we write the equation in this particular form, here we will be having like T0 is essentially an unknown. In this particular equation T0 is an unknown. So previously when we are dealing with Dirichlet boundary condition or say the Neumann type of conditions, in Neumann type of conditions this entire flux value is given, so you directly substitute that value, so that wouldn't be a big problem, so you wouldn't have an unknown there. So when you have a Dirichlet condition, this T0 will be a known value, so you don't have to solve for it. But here in this type of boundary conditions, your T0 is an unknown, so you need to somehow replace this T0 with some known value. So now we will take the boundary condition to see how that happens. So the boundary condition is given as minus k times dt dx at x equals 0 is s0 times, so let's understand this. So at x equal to 0 you have dt dx. Okay, so this will be T0 minus Tf, this is how it is given. So if you consider this, for the dt dx we will again take a linear approximation, so we have minus k times dt dx can be written as Tp minus To by, we will take the half cell, so it's essentially delta x by 2 equals Ho times To minus Tf, T0 minus Tf. So this is something you might be familiar with, that you have seen. So if I just do some little rearrangement, so if I just take this as a resistor network that you might be familiar with, so since we have a P cell, this is your 0 or say west boundary, this is your west boundary, and this is my fluid temperature Tf. This is my T0 on the west boundary. I'm just calling it as T0. So maybe I haven't used any notation. Okay. So between the Q between, so I will just call this as, so the heat flowing through this, the heat flux is essentially Q. So across these two, Q is essentially given by H times if the flow is from ambient to this one, and in this particular one Q is given by K times Tp delta x. So essentially it goes like Tf minus To by 1 over H equals To minus Tp, it's essentially by 2, so delta x over, okay, I think there is some sign change that needs to be done here, so it's k times dt dx equals Ho times To minus Tf. Yeah, sorry for the correction. Here you don't have a minus. So if you just group the terms together, you just take a summation of this, so this essentially will be equals to To minus this can be written as Tf minus To plus To minus Tp by 1 over Ho H0 plus delta x by 2k. This essentially gives you Tf minus Tp by 1 over Ho H0 plus delta x by 2k. So our objective is to get the value of Tp minus T0, so or T0 minus Tp. So T0 minus Tp is essentially equals, I'm just calling it as R0 times Tf minus Tp, where your R0 is delta x over 2k by 1 over H0 plus delta x over 2k. So now if I substitute this back into our original equation, so this is our original equation. This is our original equation. Now if I substitute this back, so I will be getting k over delta x times T east minus Tp minus 2k by delta x. So it will be a plus R0 times Tf minus Tp plus S delta x equals to 0. So now if I group the terms, so for the east I have a k over delta x. It is on the west boundary, so I won't be having any coefficient for the west temperature, that is 0. And then I have a constant term is S delta x, and there is a contribution from the boundary, that is 2k by delta x into R0 into Tf. And if I group terms for Tp, I have a k over delta x coming from the east flux and one term coming from the west flux, that is 2k by delta x into R0. So this is my east one, this is my west, this is my B term, and this is my AP term. So now if you try to do the same for on the right boundary, it should be fairly easy to, it is fairly straightforward to implement it. So instead of the east, the coefficient of the east term will essentially be 0 because it is on the right boundary, and it's like on the west face will be similar to something like the what I have done for the east face, so it will be k over delta x. Now the source term, B term, will essentially have a source term contribution, and then we have 2k over delta x into, instead of R0 I will be writing RL here, into Tf is the fluid temperature. This will be equals Tp times, now you have contribution 1 from the from the west term and 1 from the boundary condition, that is 2k over delta x into RL, where your RL is essentially delta x by 2k over 1 by HL plus delta x by 2k. So this is fairly straightforward. AW, this is your B term and this is your AP term. This is how you treat when you have mixed boundary conditions, and this is how practically most of the problems will be set up in. You will be given your heat transfer coefficient and you will be given an ambient temperature, and you should write your equations in this particular form. So we have got the equations and we have discretized it. So the third question asks about the convergence of Gauss-Seidel method for steady state heat conduction equation without any source terms under different types of boundary conditions. So this is essentially about your algorithm. So for convergence of any iterative algorithm, or in particular Gauss-Seidel method, if our equations are of the form AP Phi equals sigma A and B Phi and B plus B, if the equation of this particular form, then the criteria is the Scarpero criteria says that the value of sigma A and B divided by AP should be less than or equal to 1. Only then convergence happens. If this particular criteria is satisfied, then you can rest assured that convergence happens. If it is not satisfied, even then convergence can happen. It is not an if and if type of condition. So if this condition is satisfied, then convergence is assured. Even if this is not satisfied, convergence may or may not happen. So now let us see how your boundary condition affects this convergence rate. So the question asks you about steady state conduction without any source terms. Say we will consider a 1D problem. So the governing equation is essentially d dx of k times dt dx equals 0. So the discretization is again fairly straightforward. So we take a cell, it's my P, this is my east cell, this is my west cell, my west face, this is my east face. So if I discretize over this, so I have I'll be having from west to east ddx of k times dt dx equals dx equals 0. So this will again give me k times dt dx on the east face minus k times dt dx on the west face equals 0. So this will again come to k over delta x times t east minus tp minus k over delta x tp minus t west equal to 0. Now if I group the terms together, the equation is something like k over delta x times, so for the coefficient for t east, and for the west we have a coefficient of k over delta x, and for tp we have a coefficient of 2k over delta x. So this is for the interior cells. Say the first question asks you about the Dirichlet condition. So for Dirichlet type of condition, so for all the interior cells, so now let's say what happens for all the interior cells. So if you take the value of sigma a and b, so that is essentially your east plus west, that is equals k over delta x plus k over delta x, so that is 2k over delta x, and that is essentially equal to your AP. So your AP is also equal to 2k delta. So as per the original criteria, it should be less than or equal to 1. So it should satisfy both the equality as well as the inequality constraints. So for all the interior cells, the equality constraint is satisfied. Now let's see what happens on the boundaries. So the first boundary type is say Dirichlet. So now when you have a Dirichlet condition, it is something of this sort. So say suppose we are taking it on the left boundary. This is my east cell, this is my east cell, this is my west boundary. So if I write my equation over here, so the equation is again straightforward. So dt dx over the east face, this is my east face, minus dt dx over the west face should be equal to 0. On the east face it is straightforward, so we just take a linear profile assumption, so we get east minus p. And on the west face, now we have a Dirichlet condition, so we will be taking like tp minus t west boundary, by instead of delta x we just have an half cell, so it will be delta x over 2 equal to 0. So in this particular case, what will happen if you group the terms? For the east coefficient is k over delta x. Now we don't have a west coefficient, this is essentially 0, and there is a b term, so 2k times t west boundary by delta x. If you group the terms for p, we have a k over delta x from the east flux and 2k over delta x from the west flux, that amounts to 3k over delta x. This is my east, this is my west, this is my b term, and this is my AP term. Now if you try to apply the Scarpero criteria, what do we get? So if you just take sigma a and b, that is east plus west, we don't have a west term, we just have an east term, so this is k over delta x. Now if you take the value of AP is 3k over delta x, so it is like sigma a and b is less than AP, so the inequality constraint is satisfied here. So if you have at least one Dirichlet condition, then in that particular case the inequality condition will be satisfied, and this will ensure your convergence. Now let's see what happens when you have a Neumann type of condition. It's like an adiabatic condition. So I'll just simply put it as an adiabatic condition. I'm just taking an adiabatic case, but it will be similar for even if you have a constant flux. So or maybe then I should take it for a constant for a Neumann condition, or say we'll just go with the simple case, the adiabatic case. So in that particular case, we just take the same cell as before. This is my P, this is my east, this is my west boundary. So now that it's not a Dirichlet condition, we don't know the value of the west boundary, but one thing we know for sure is on the west face the flux is essentially 0. So this term is essentially 0. That is the adiabatic condition. So we expand this. So on the east place the flux will again be Tp minus Te equals 0. So now if you just group, sorry, it should be the other way around. Maybe I'll just put a minus here. So the terms are like, if you group the terms for E, it will be k over delta x plus the west face is essentially 0. You don't have a B term, and Tp term is essentially k over delta x. So this is my A east, my A west, this is my B term, and this is my AP term. So now to apply the Scarborough, if we see the sigma A and B, that is, here we just have two neighbors, east and west, that will give me a value of k over delta x, and AP is also k over delta x. So this is essentially equal to AP. So now if you have all the boundary conditions as Neumann conditions, or essentially all the boundaries are either adiabatic or constant heat flux, then in that particular scenario you will have only equality being satisfied, and your inequality will not be satisfied, and as such your convergence is not guaranteed. So let's say we have a mixed condition, something like the one we have discussed just now. So you have a heat flux, not a heat flux but a convective kind of flux, where you are given the ambient temperature and the heat transfer coefficient. So it is something as, so we will just take the same cell. This is my east cell, this is my P cell, this is my east face, and this is my west face. Now on the west face, what is given is, it's mentioned like k times dt dx on the west face is essentially given as a function of heat transfer coefficient and some reference temperature, or say ambient temperature. It is given in this particular form. So if we take our original equation, we have dt dx. So it's the same steps as before. So this will again come down to k times on the west face Tp minus Tw, or W is what I am calling as T0. Just stick to the notation. So instead of Wb, I am just calling it as T0 by delta x by 2 is equals T0 minus Tf by 1 by h. So this will kind of come down to Tp minus Tf by 1 by h plus delta x by 2k. So this is similar to what we have done before. So from this what you get is k by, so now you have an expression for this term essentially equal to this term over here. Now if I write our original equation, so we have k dt dx on the east face minus k dt dx on the west face equal to 0. On the east face it is k over delta x, so this should be kind of much familiar now, minus on the west face. Now this I am replacing with the last term, so that will be Tp minus Tf by 1 by h plus delta x by 2k equals 0. So this will give me, if I group the terms, the east term I have k over delta x, for the west I don't have any coefficients, and for the constant term I have something like 2k h by k plus h delta x into fluid temperature equals, now for the Tp I have two terms, one coming from the east and one coming from the west boundary. So from the west boundary I get something like 2kh by h delta x plus k. So this is my A east, this is my B term, this is my A west term, this is my AP term. So again if you try to check the Scarborough, so we have sigma A and B, so we have two neighboring points, so that is east plus west. So here there is no west coefficient, so this will give me a value of k over delta x. If we try to compare with the value of AP is strictly greater than this, because if you consider the second term out here, so 2kh by h delta x plus k, since both k and h are positive values, this term will be a positive value. So your AP will always be greater than, as long as your h is not equal to 0, in which case this will be equal to the previous one. If h equal to 0, then this condition will be similar as the Neumann condition. So except for that particular case, in all other remaining cases, AP will be strictly greater than sigma A in B, and your Scarborough is satisfied, so that your convergence is guaranteed. So that is to do with the third question. So now let's come to fourth one. So here we have a 1D steady diffusion in a material with two different diffusion coefficients and without any source or instance. The domain is discretized in such a way that your cell phase occurs exactly at the interface between these two materials. So what will you take the value of gamma at the interface? It can either be arithmetic or harmonic mean. So how will we go about it? In either of these cases, the question asks you to find the heat flux at the interface. Okay. So it should be fairly straightforward. So you have a material. So essentially you have two different materials. So this is a material. So to the left hand side you have say gamma 1, here you have gamma 2. So it's a steady state equation. Say we'll consider 1D case, gamma t phi dx, phi is my variable, equals 0 without any source or sinks terms. So this is my governing equation. So we'll not worry about the boundary conditions as such. The question asks you about the interface. So this is exactly my interface. At the interface, the discretization is done in such a way that your interface falls at a cell phase. So essentially when you are discretizing the above domain, it's chosen such that your phase is exactly matches with the interface. So this is exactly an interface. This interface is exactly this phase. Say suppose I am on to the left of this. So if this is a cell I am trying to write the governing equations for, discretized equations for. So this is my east cell, this is my west cell, this is my east face, this is my west face. So it's again fairly straightforward. So you just start with from west to east, you integrate the equation d dx of gamma d phi dx times dx equal to 0. So you get gamma east d phi dx on the east face minus gamma west d phi dx on the west face equals to 0. The question now is gamma west is fairly straightforward. So everything towards this side has diffusion of gamma 1 and everything towards this has the diffusion of gamma 2. So gamma w on the west face, on this particular face, is equals to gamma 1. So that is fairly straightforward. The question is, what is the value of gamma e that we should take? If you took towards the left, it is a gamma 1, and if you took towards the right, like this, essentially you have a function which is discontinuous at that particular phase. So which is what value do we have to take for gamma? So the criteria here is, so how do we decide which value is correct and other is not, is we go with the heat flux. So the gamma you are choosing, whatever gamma you are choosing should give you the same value of heat flux that it gives you at the other phase. So what I mean is, so if I take, I can apply a discretization this way. So this is my p cell, this is my east phase. So the heat flux can be calculated in two ways. So the first way is essentially Q equals gamma, I can just take as gamma 1 times, for d phi dx I can just approximate phi east minus phi p by delta x over 2. I can write it this particular way, or there is a second way where this is my p cell, this is my east phase, this is my east cell. So it's the same Q that has been flowing. So I can write the value of Q as gamma 2. This is in the second medium, gamma 2. This is gamma 1 and gamma 2. So here you have gamma 1 and gamma 2. So the second I can write it as gamma 2 times phi capital E minus phi little e by delta x by 2. So this I am calling Q1, this I am calling Q2. Alternatively, there is a third approach where you have this as a P cell, this as my E cell, E phase, and this is my E cell. I can write Q3 as gamma is, I don't know what is the value of gamma that I have to choose, into times phi capital E minus phi capital P by delta x. This is the equation that we have been following till now. The only difference is what is the value of gamma E. So the criteria says that whatever value you choose among all these three options, you should get the same value of flux. So if you want to get the same value of flux, that is the value of gamma that we have to choose. So what I mean is, find gamma E such that Q1 equals Q2 equals Q3. If I just write these equations, so I'll get something like phi capital E minus phi capital P by delta x over gamma E equals Q2 is phi capital E minus phi little e by delta x over 2 gamma 2, and that equals Q1 is essentially phi little e minus phi capital P by delta x over 2 gamma 1. If you take these two equations together, we get something like phi capital E minus phi capital P by 1 over 2 delta x by gamma 2 plus delta x by gamma 1. So what are we getting here is delta x by gamma E equals half x by gamma 1 plus delta x by gamma 2. So this will essentially give you gamma E as 2 times gamma 1 gamma 2 by gamma 1 plus gamma 2. So this is your harmonic mean. So what this means is, if you consider a harmonic mean of both the mediums at the interface, then in that particular case your heat flux will be same with your heat flux will be same if you consider from either of these directions. So there could be another way that essentially instead of going with the harmonic mean, you can just go with an arithmetic mean. So what happens if you do that? So basically what I was trying to say is, you have so we just take the cell again. So this is my east, this is my P, this is my E. What are we trying to say is, I define my Q as gamma east. So it is the same expression, but instead now I am saying gamma E, I can take it as an arithmetic mean of both the discontinuities. So I can just take it something like this. So what happens if you do this? So if this is the heat flux, so we will try to compare this with the heat flux that we obtained previously. So in this particular scenario, what we have is gamma 1, this is gamma 2. So the actual heat flux, so you have Q as gamma 1 plus gamma 2 by 2 delta x to phi capital E minus phi capital P. But we know the actual heat flux on the west face is given by, the heat flux is given by gamma 1, like if you go along this direction, it can be written as phi little e minus, so if it goes to the same derivation, so phi little e minus p capital P by delta x over 2. So if you try to find out the difference between these two, so this is exactly not equal to this. Or maybe I can give you a better example, or a simple example, where say you have an arithmetic mean and harmonic mean. So your gamma E is essentially given by gamma 1 plus gamma 2 by 2. Here you are given as 2 gamma 1 gamma 2 by gamma 1 plus gamma 2. So you have an insulator towards your right. So essentially I am saying gamma 2 equal to 0. So if your gamma 2 is essentially 0, what should happen is, you have something like this. So you have a material where this is essentially your insulator. Gamma 2 is essentially 0. So what does that mean? At this particular phase, your flux going along this direction should be 0. There shouldn't be any flux inside the insulator. So but what happens here when you do the arithmetic mean? is you get a value of gamma 1 by 2. Now here it is 0. So this is actually depicting the real case than the other one. So harmonic mean is usually used in compared to the arithmetic mean, because it is kinds of satisfies your field flux condition. Now let's come to the fifth question. It asks you to solve the conduction equation without any source or sink terms, but here the only difference is your thermal conductivity is not constant, it is a function of temperature. So this is what we have been discussing previously. So you have your differential equation where your coefficient is a function of the unknown. So here the unknown is the temperature, and your coefficient is also a function of temperature. So these type of equations are what we call the nonlinear PDEs. And then the conditions are given on Dirichlet conditions. So you have on the left boundary the value is 0, and on the right boundary you have a value of 1. The question asks you to solve using discretize using FBM and then obtain the expressions for them. So the nonlinearity is something we have answered now. So we have to solve them using Gauss-Seidel method and then compare the solutions using different kinds of means. So we'll just see how to go about with this. So the governing equation is again straightforward, ddx of k dt dx equals 0, and the boundary conditions are at x equal to 0 we have 0, x equal to 1 we have 1, and we are given k equals 1 plus 2t. The analytical solution is quite simple to find it out, so you can compare once if you code your finite volume method. So yeah, before doing that, so let's see how this goes off. So the first step as always is to take your domain and then discretize it. I'm discretizing again using phases. So first I'll define my phases and then take the phase centroids. This is how I discretize them. So this is my ith cell, I minus 1, I plus 1, or we'll stick to our original notation. So we'll consider for any interior cells, we'll start with interior cells and then we'll go to boundaries. So for any interior cell you have something of this sort, where you have a pith cell, you have an east face, east cell, west face, and a west cell. So we discretize these equations along east to west, ddx, or okay, it should be the other way around. So west to east face, k dt dx, dx equals 0. So what this gives me is the k times dt dx, the east face, minus k times dt dx on the west face equals 0. So this k over here on the east face is ke times t east minus tp by delta x, and similarly on the west face I am writing as kw times tp minus tw by delta x. So if I just group the terms together, so for the east coefficient I have as ke little e, and for the west I have k little w equals tp times k little e plus k little w. The only problem here is this k little e is a function of temperature. So what is k little e? As per the equation it is 1 plus 2 dE, but the notation we are following is we are storing the values of temperature, or we are finding the values of temperature only at the cell centroids and not at the phase centroids. So this t is essentially unknown. So if you see back here, so even after solving we will only get the values of tw, tp and te. These are what that are being stored. T little e is something that we don't know. So one approach is to essentially approximate it again. So you can just take a Taylor series expansion of t little e. So t little e is essentially can be written as tp of x plus let x by 2. You just expand over around tp. See, so this is my p point and this is my little e and this is delta x by 2. So what I am saying is if you expand around the p point, so t little e can be written as tp plus delta x by 2 into dt dx evaluated at p plus some higher order terms. So again, for dt dx, we'll approximate a linear case, linear approximation. You have t capital E minus Tp by delta x. So I'm just ignoring the higher order term. So this will give you Te plus Tp by 2. So one approach is to essentially approximate this in this way. So that you have your phase temperature in terms of your cell centroids. Cell centroids are the only ones we know. So if we do this, what happens? So the term as k dt dx on the east phase is essentially ke times Te minus Tp by delta x, where your ke is again Te plus Tp. Okay, sorry. So this will be 1 plus 2 times Te is Te plus Tp over delta x. So now you see the nice form we were obtaining. So if we do the same for on the west phase, the resulting equation will be something like 1 plus Te plus Tp times Te minus Tp minus 1 plus Tw plus Tp minus Tw equal to 0. So this is essentially a nonlinear equation. So till now we have been obtaining only linear discrete equations, but if you try to solve in this particular, you will be obtaining something called a nonlinear equation, and then this should be solved using some other methods like Newton-Raphson. So how do we go about this? So our aim is to essentially linearize this equation. So what we are linearizing it is again based on a Taylor series expansion, but now it's slightly different. So what we are trying to do is we will guess the values of Ke. So the original equation we were having is Ke times Te plus Kw times Tw equals K little e plus K little w times Tp. So here, since we are replacing the K value as a function of temperature, the equation became nonlinear. So what we will do is we do not replace it as such, but instead we will define K star, where this K star is the value evaluated at the previous iteration value of the temperature. So like in the Gauss-Seidel loop, when we are trying to solve these equations, when we take initial values of temperature, you take those initial values. So essentially the procedure will be something like you guess initial values, you guess an initial temperature field, and then you evaluate the coefficients. So essentially you evaluate K star with the guess field. So say this is T star. So assuming this T star field, you will evaluate the values of K star, Kw star, and with those coefficients you solve using Gauss-Seidel, and then once you solve, what you get is a new temperature field. So this is the solution. So this is my solution. What I do with the solution, again I substitute the solution for the initial temperature field, and then this process repeats. Now T star will be replaced by T, and with this new value of T star, again I will evaluate K star, I will evaluate the coefficients and then solve the equations, and again this process keeps on going till the point where your difference between T star and T is within your tolerance. So whatever tolerance you have specified. So at convergence, your T star will essentially be equal to T, so you don't have a problem then. So this is the way how we try to linearize your equations. So maybe after going through all the problems, we'll actually see how to implement it in the code. Okay, now let's come to another question. This is again a standard question where you have a Laplace equation with the given boundary conditions. We need to find the analytical solution as well, and then we need to compare it with the FEM solution. Okay. So the domain is, so it's a square domain. You have the boundary conditions here. So this is essentially xy equal to 0 equal to 0. Here you have x equal to 0, y equals 0. You have x equal to 1, y equal to 0. And here you have x comma y equal to 1 as 1. The equation is again straightforward. It's just the Laplace equation plus del square d in 2 dimension. So the first part is essentially to find analytical solution. So for those of you who are not aware of solving, so this is a second order PDE. So you start with the method of separation of variables, where you assume t of x5 to be a function of to be a product of two functions, f of x times g of y. So substitute here, it is f double prime g plus f g double prime equals 0. So this will, if you rearrange these equations, so it will be f double prime by f, and you need to know your boundary conditions as well. So we'll just come to boundary conditions now. So the boundary condition essentially is t of x comma y equal to 0 equals f of x into g of 0 equals 0. So to avoid the triviality where f of x equal to 0, so our boundary condition on g is this. Now similarly you have x equal to 0 comma y equals f of 0 times g of x, that's essentially 0. Again, to avoid the triviality, so you should have f of 0 equal to 0. Similarly you have x equal to 1 comma y, so give you f of 1, so this should be g of y. Again, to avoid the triviality where g of y equal to 0, you have f of 1 equal to 0. And we have the final condition, x comma y equal to 1. This will give you f of x times g of 1 equals 1. So here we don't have anything to say, okay, but we'll come to that later. So now we'll take this original equation. So if we just rearrange this equation, so I'll get something like f double prime by f equals g double prime by minus c. So this is purely a function of x, and this is purely a function of y. So you have something which is purely a function of x and something that is purely a function of y, and the ratio should be equal. It's only possible if you have it equal to some constant, just saying lambda square. So your equation becomes f double prime minus lambda square f equals 0. The solution of this equation is this is the wave equation. So you have f of x equal, say, some a times, or maybe I will just say f1 times sin lambda x plus f2 times cos lambda x. Now if you substitute the boundary conditions, so f of 0 will give you f2 equal to 0. If you substitute f of 1, this will give you f1 times sin lambda equal to 0. Now if in this case, if you just consider f1 equal to 0, that will give you a trivial solution. So the other option is to essentially have lambda equals n pi. So these are essentially your eigenvalues. So now you have something like f of x is essentially, it's a summation of sigma, so I'm just saying, so we will just say a n sin lambda n x, where essentially your lambda n is n pi. Now let's come to the other equation. The other equation is g double prime plus lambda square g equals 0. So this is where you have g of y given by, say, some g1. You will have your hyperbolic functions sin h of lambda y plus g2 cos h of lambda y. So now, or maybe you can just take the exponential constants if you are familiar with that. So the solution will be something like g1 e power lambda y plus g2 e power minus, where g1 g2 are essentially some constants. So we have only one condition on this, so that is g of 0 equals g1 plus g2 equals 0. So we have g1, okay, that is one equation. So if you substitute it back into g of y, you can write it as some constant g1 times e power lambda y minus lambda y. I can just write it as 2 times c1 sin h of lambda y. So now the total solution t of xy can be written as a series solution, where you can write this as sigma a n. Your fx is essentially sine of lambda n is n pi x, and then along the y you have a sin h function, hyperbolic function of I'll just write lambda with n pi y. So now we have the last boundary condition where x comma y equals to 1 equals, substitute it here, so x remains the same and y equals to 1. So this is n pi x into sin h of n pi should be equal to 1. So the only unknowns are essentially your an. So this is obtained by your orthogonality property. So essentially what you do is it's something like you just integrate over sin n pi x. So you just multiply with sin n pi x and you just take an integration over both the sides. For all the terms where n is not equal to m, you essentially end up with a 0. That is the orthogonal property of these sine functions. So what you get over there is an times integral 0 to 1 sin square n pi x. Then you have sin h n pi dx equals, on the right hand side you have, you just multiply it with sin n pi x dx. So here you have an sin h n pi. So this can be written as 1 minus cos 2 n pi x so this will be cos pi x. So if you just simplify this, you have an sin h n pi into so the other term will go into 0, so you will be left with a half. So for the cos h it will be 0. So here you have 1 minus cos n pi is essentially minus 1 over n, minus 1 power n by n pi. So now you are left with an expression for an equals 2 times 1 minus minus 1 power n by n pi into sin h of n pi. So you see the term over the denominator, the sin h is essentially will keep on increasing as a function of x, and then the n pi over here is 1 over n pi. So as you keep on increasing n, these terms will keep on decreasing. So essentially what happens is as your n increases, your an will be kind of decreasing. So you need to consider only like first few terms to be able to accurately evaluate your function value. So for the purpose of demonstration, maybe I will show the code at the end of the session. I have considered around 10 terms and that gave you like quite a good accuracy. So now let's go to our method. So we'll try to find the solution using the finite volume method. So process is again straightforward. So unlike the 1D case, here we have a 2-dimensional problem. So the discretization will be something slightly changed. So instead of just 2 neighbors on the east and west, now you have 2 more neighbors, one coming up on the north and other on the south. This is your P, east cell, west cell, north and south cells, and accordingly you have your east face, north face, west face and south face. So now I will be writing the equation for the each cell. So it's again the same equation. So the governing equation is d square t dx square plus d square t dy square equal to 0. So if I take an integration over here, what it happens is this will boil down to having fluxes over each and every face. So if you are familiar with vector calculus, it is something like you have divergence of grad t dv will essentially give you summation of grad t dot n cap into af, just taking over faces. This is what I will be using. So if you take on the east face, you have something like grad t on the east face is del t del x. So maybe I'll just do for one face and it will be similar. So suppose on the east face, you have grad E as del t del x I cap I hat and del t del y j hat. So the flux term is essentially grad t times A east. So this is essentially del t del x I hat plus del t del y j hat dot. To the east face it points towards the right, the area normal points towards the right, and the area is essentially dy times I hat. So this will essentially give you del t del x, sorry, this will give you del t del x times delta y. So similarly, if you do the fluxes in all the phases, so it's essentially del t del x on the east face times delta y. On the west face it will be opposite, so it will be minus delta y. Similarly on the north face, again the gradient vector is in the direction of the area normal, so del t del y times delta x, and on the south face it will be again opposite, so del t del y on the south face is delta x equal to 0. Now when we use a linear profile assumption, so on the east face this will be equals t east minus tp by delta x times delta b minus tp minus tw by delta x times delta y plus t naught minus tp by delta y times delta x minus t e minus t south by delta y times delta x. So now again the similar way we group the terms together. So for the east I have a term delta y over delta x. For the west I have a delta y over delta x. And for the north I have a delta x over delta y, and for the south I have delta x over delta y, and I take p towards the other side, tp. So you have 2 times from the east and west faces and from north and south faces. So this is essentially my A east, this is my A west, A north, A south. I don't have a p term here, so this is essentially AP. So the equation, the form of the equation remains the same. So here you also you have AP times TP is sigma A and B, where your neighboring points. Now instead of east and west you also have north and south. That's going to be the only difference. So it will be A and B, T and B plus B. Now let's try to apply the same for the boundaries. So this is for the interior cells. Now for the boundaries. In 1D case we just have 2 boundaries, but in the present case we have 4 boundaries. So on the left boundary, this is my peach cell, this is my north, south, east, north face, south face, east face, and this is my west boundary. So it again the equations remain the same. So our original equation is del t del x on the east face minus del t del x on the west face plus, okay, forgot to add the areas, so it's essentially delta y times del t del x on the east face minus delta y times del t del x on the west face plus delta x times del t del y on the north face minus delta x times del t del y on the south face should be equal to 0. So here on the east face it is again straightforward, so you just put t east minus tp by delta x. Now coming to west face, it's similar to the one previously we have done for 1 dimension. So we'll write only till the boundary, so it will be tp minus t west boundary by Instead of delta x, now we just have a half cell, so it will be delta x over 2 plus delta x times on the north is again straightforward, so it's t naught minus tp by delta y. On the south again it is straightforward, so it is tp minus ts by delta y. So if you group the terms together, so you have east comprising of delta y by delta x, and since it is on the west boundary, you don't have any terms contributing from west coefficient. On the north you have a delta x by delta y. On the south you have a delta x by delta y. Now you have a source term coming because it's a Dirichlet condition, you will be having a source term, so that is essentially 2 times delta y t west boundary by delta x. So this is your b term. Now if we group the terms for tp, you have 1 delta y by delta x coming from the west face, 2 delta x by delta y, 1 from north, 1 from south, and another 2 delta y by delta x. This is essentially coming from your Dirichlet condition on the west boundary. So this is your a east, a west, a north, a south, b term, and this is your ab term. So again the equation of the singular form. Now the same thing applies for on the east boundary, north and south boundaries as well. So instead of say, maybe I'll just write for say north boundary. So your TE will essentially have the coefficient delta y by delta x. Your west will also remain the same, delta y over delta x. Now since you are having on the north boundary, you won't have any coefficient coming from there, and for the south boundary you have the same delta x over delta y. Now you will have a b term coming from the north Dirichlet condition, so you have delta x t north boundary by delta y equals tp times you have 2 delta y delta x and then 3 times delta x by delta y. Now I think it should be fairly straightforward. I can write the equations for other boundaries as well. So for the south boundary, again you have the east term will be there, it will be delta y over delta x. The west term will also remain the same, delta y over delta x. The north term will also remain the same, so that is delta x over delta y. Now since it is on the south boundary, I won't have any coefficient from this, but the term will be added to the constant. So 2 delta x over delta y times south boundary value equals tp. The value of AP will essentially be same for both the north and south boundaries here. Now similarly you can write equation on the east face as well. So for the east boundary, maybe so since it is on the east boundary, you shouldn't have any coefficient for the east. Your west will be here now, but your south will essentially have the same coefficient, delta x by delta y. Now since it is a east one, the constant term will be in terms of east boundary, so you have 2 delta y by delta x times east boundary value, and your TP coefficient will also change. So now you have 2 times delta x by delta y coming from north and south, and 3 times delta y over delta x coming from east and west. So these are the governing equations for all the interior. So these are for the boundary cells, and the previous equation you obtained, this is for the interior cells. Now you see, since it is a Dirichlet condition, you can kind of directly verify from here the sigma A and B value in this equation is equal to the AP value. So the equality is satisfied for all the interior cells. Now when it comes to the boundary cells, because of the Dirichlet condition, the sigma A and B, maybe we'll check for the east phase for just for one phase. So in this case, if you calculate the value of A and B, which is A east plus west plus north plus south, that will essentially give you 2 times delta x by delta y plus delta y by delta x, which is strictly less than the value of AP. So the convergence is kind of assured. So the previously we have just derived for a 1D case, but it kind of applies well even for 2D and 3D problems. So for a T-step boundary condition, you will necessarily have your convergence is kind of assured with the causative. So now since we have now that we have the equations and we also have the boundary conditions, we can solve this using either cos theta or any of the direct methods. Let's go to the last question. The last question asks you to solve the same problem, but instead it is told that your material is an anisotropic medium. So essentially you have different values of kx and ky. So your governing equation now will be suppose you have an orthotropic material, so this is your governing equation. And your boundary conditions remain the same, so it should be fairly straightforward. The only difference will be in your coefficients. So I will be just writing the equations for the interior cells, so you can just explore. It will be straightforward to implement the boundaries as well. So we will take for interior cells. North, P, south, east, west, have an east face, west face, north and south faces. So when we are discretizing this, same like the previous one. So for the east face, our flux is given by, so it's like del T on the east face dot A east, so which is essentially maybe I should write it, just be careful. So QE times AE. So your QE is essentially Kx del T del x plus Kx del T del x I hat plus Ky del T del y j hat times your AE is essentially dy, or maybe I should say delta y times I hat. So this will essentially give you Kx del T del x on the east face. Now you can kind of do the same for all the faces. So what you will essentially get is something like Kx times del T del x on the east face minus Kx del T del x on the west face plus Ky del T del y on the north face minus Ky del T del y on the south face equals 0. So if you just take the same linear approximation as before, so I'll just group the terms together and directly write the equations. So for T east, I'll have Kx, so there should be a delta y here, and a delta x here. So Kx delta y by delta x plus the same for west coefficient, Kx delta y by delta x. For the north coefficient, we have Ky delta x by delta y, and for the south coefficient, we have Ky same as the north coefficient, and this should be equals to Tp times you have 2Kx delta y by delta x and 2Ky delta x by delta y. So the only difference is now you have two different values along your A east. Your A east and A west will have one value of thermal conductivity, whereas your A north and A south will contribute to different values. That's going to be the only difference in case of an anisotropic medium. So in the question it is given as the Kx value as 1 and Ky value as 5. You can substitute these values and then you can get your equations. Yeah, now since we have covered the equations part, so we will go to the implementation part of it. we'll go one by one. So the first question was on the Finn equation. So in the Finn equation, it is a 1D equation. So it's the same code that we have been discussing in the previous week. So this is where you set your problem. So these are just some input statements, and you have defined Tx as n, where n is your number of grid points. Tw is your west boundary, that is the theta value at the west boundary. Since it is an isothermal base, you have the west boundary given as 1, and it's an adiabatic one, so I don't need any boundary condition specifically as an input. So it goes into the solve problem function. So what happens in solve problem is essentially you update your coefficients. So these are the coefficients we have obtained previously. So your A west will be equal to 1, A east is equal to 1 for all the cells except for the boundary cells, and your AP will have in addition to a constant term, you have a term as 2 times delta x square. So this is essentially coming from the source term, so that is your coming from your Finn parameter term. So it's m square times theta. So this is where you get that expression from, and your B is essentially 0 everywhere. You don't have any other source terms. So again on the boundaries, on the west boundary you keep W equal to 0, and then you accordingly update the value of B, and similarly on the east boundary you have 0. So here if you observe the value of AP so everywhere it is kind of made in this particular fashion, so kind of make everything equal to 0. Okay, so exactly at the value of maybe it should be 3 coming 1, so it's on the left boundary you have a Dirichlet condition, so you will be essentially having 2 terms, one coming from the east face, so that is 1 coming from the A east, and a 2 coming from, maybe I'll just split this, so a 1 value coming from the east face plus a contribution of 2 coming from the west face, and then you also have something to do with the constant term. So it is essentially the m times theta, so that is essentially 2 times okay, that goes into your B term. So this is 1 plus 2. So maybe I should just show you the equations, or it should be fine. So you have a 1 coming from the east face, a 2 coming from the west face, and then you have a 2 times this last term is essentially coming from your source term in your equation. So this is as such the 2 times theta p term. So if you just take the theta p common, so this is what you will be left with. So this is your B of 0. Again, since it is a Dirichlet type of condition, the term gets added to your source term as well. So that is 2 times TW. TW is a west boundary condition which is given as well. And similarly on the east boundary is a normal condition. So your A east to the east will be 0, and AW on the last cell is essentially equal to 1. So AP is again, instead of value of 2, now you will be having a value of 1. 1 got reduced, and then you also have a term coming from the source. So now after this you just pass it through your Gauss-Seidel. So Gauss-Seidel algorithm is again the same. So you define some tolerance. So what it does is for the boundaries you just calculate the value of this. So A is times Ti plus 1 plus Bi by Ae, and then you update these values. You keep on iterating till your error is the value obtained from the previous value of the temperature field versus the current value. So the difference, if it is below within a certain tolerance specified by you, you just stop the iterations. So this is the Gauss-Seidel implementation. Just run this. So this is the convergence. So maybe I should show you the analytical part as well. So for an adiabatic tip, you already know the analytical solution. So I just tried to compare the actual solution with the analytical one. So if you can see here, for a very low number of grid points, so I think around 20 number of grid points, it kind of already converged with the analytical solution. So the line over here is analytical solution. The cross marks are for very low grid value points of 2. So even for grid number 5 number of grid points, with just 5 grid points, it kind of converged to the analytical solution. And even as I increase my number of points, it is kind of converging. So this is what you do for a grid independent study. So we'll go to the next question, is where you have this is the second question we have been discussing in the same it's similar to a 1D steady state heat conduction equation. The only difference is here you have your conductivity as a function of temperature. So what do? I take another I define another function here which is a function of temperature. So that is 1 times 1 plus 2 times t, where is a function of temperature. Now how do we solve it, like I have been discussing previously? To solve this equation, the Gauss-Seidel method remains the same. The only difference comes in this, okay, maybe we will see the boundary conditions also. So the west boundary condition is 0 and east boundary condition is given as 1. So all other parameters remain the same as the previous question. The only difference here is in the previous question, if you were to see the previous question, inside this function, all the coefficients are defined first, and once all the coefficients are defined, then you go and solve your Gauss-Seidel process. But when you have your coefficients as a function of temperature, the only difference you will be making is you will update the coefficients as you solve your Gauss-Seidel method. So now, though the coefficients are initialized here, the coefficients will be updated inside another loop. This loop will ensure the difference between the guess temperature field and the value of temperature field obtained after Gauss-Seidel iteration is not changing within the tolerance limits. So you assume some temperature here, so T is your initial assumed temperature. Tnu is something that you get after you solve your Gauss-Seidel method. So what I did, initially both of them might be equal. So you update your coefficients based on the guess value of temperature. You get all the coefficients and then you solve the Gauss-Seidel method and store it in the Tnu variable. Now you find the difference between the new versus the previous one. So I've just taken L2 norm, you can use any other norm. So the Tnu minus T, you get the other value. Now what you do is replace your current temperature field with the temperature field obtained from the Gauss-Seidel method, and then the loop again starts. So this will kind of repeat till it converges. Again, to obtain the values of k, since it's again something similar to having two different media, so I have k1 and k2, I have used a harmonic mean kind of way. You can as well use arithmetic or something, it shouldn't be affecting anything. So but as we have discussed previously, harmonic mean will ensure you that the flux will remain conserved. So I have run the solution already, so maybe I can show you the solution directly. So that can be solved analytically. So I have compared the solution from the finite volume method with analytical method, and both of them are kind of agreeing well with each other. You can see that here. So this is for the case of linear diffusion. Now we can implement the same using geometric mean or arithmetic mean and then see how it kind of changes. So let's go to the final equation. So left place. Now for a 2D problem, if you find this particular class, so you will have the following variables. You need to define your grid's dimensions along nx and ny. But unlike the 1D problem, I would like to store all the variables in a 1D array. So now I need to know the mapping from your 1D array to the two-dimensional grid. So now I am adding two more variables. So this I and j will essentially, so if you have a grid point I comma j, that will be mapped to a 1D array. So if the index in the 1D array is a little k, so it should be capital I of k will give you the ith in row value of that particular cell. Similarly, capital J will be giving you that column value. So now in addition to AP, AE, north and south, I am storing another values of F north, east, west and south. So these are essentially the phase values. So for a given cell P, so for a given index, Fn will tell you which index will come to the north of that particular index. Now since I am storing in a 1D array, I need to keep track of all of this. Maybe I will explain it through. So what I'm trying to do is, say you have 2D grid, something like this. So your I goes like this, and your j goes like this. So each point is I comma j. So you have this as 0 0, so this will be your 0 1, sorry, so this is your 1 0, 2 0, and so on. So what I am saying is I am not actually storing the values in the two-dimensional array, so instead I am storing it in a single array. Something like this. Now I need to find a mapping with this. So this is my 0 1 2 3 4 5 6. So all the 9 cells over here, how am I arranging it? So I'll put a different color. So this is my 0, this is my 1, this is my 2, and once I reach the end value, I'll go over here 4 5 6 7 8. So this is how I am defining. So these are my k values, these are my I and j values. So I want to link, I want to create a mapping between, given a k value, I need to know the values of I and j. I need to know the values of I and j and the inverse mapping. If I was given the value of I comma j, then I should be able to find k so that I will be able to retrieve it from here. So this is the mapping that I will be defining here. So that is exactly the thing I have done here. So see, updating phases essentially goes from I equal to 0 to whatever is the number of columns I will be having, and once I reach that particular column, I will update the value of k as a times j plus I, and then all the phase values will be given corresponding indices. Now the only point is, if it is a boundary, say if it is on the bottom phase, say if it is on the rightmost boundary, then you don't have an east phase to it. So in that particular case, I am just assigning a value of -1. Because the indices start from 0 to n minus 1, a value of -1 indicates that it is on the boundary. That particular cell is on the boundary, and it doesn't, depending on which of the phases is -1. So if you have east phase value as -1, then it means it's on the east boundary. If you just have both east and north, then it is on the northeast, and something similar to that. So once I define all these, initialize all these values, update my phases. After updating the phases, the next step is to update your coefficients. You need to determine the values of coefficients. So delta x is essentially your length along x direction by nx. So here I might have to find length and width separately. So one of them will be L, the other one will be W. And then x and y are some variables, and this pi is this 2 a cos. So it's this cos inverse of 0 will give you pi by 2, and this will give you the value of pi. So this get cell is just a helper function. So if you want to know a value of x at some given cell, you will get this value. So this essentially is I plus half into delta x. So how do we update the values of coefficients? We know the values of ai is kx times delta pi by delta x everywhere except on the boundaries. So when it is equal to -1 is where you have boundaries. So essentially at the boundaries you should have the coefficient as 0. So this is what the statement says. Similarly you do for a west, a north and a south, and initially you will declare all the values of b to be 0, and then you will keep on updating them depending on your source terms. And in the case of Laplace equation, we don't have any source terms, so this is essentially 0. Now your AP equal to sigma A and B. Since we don't have any source terms, we won't be having any terms here. Now once we are done with updating all the interior cells, now we need to update our boundary cells. For the boundary cells on the east boundary, see we have an Dirichlet condition. So whenever we have a Dirichlet condition, we will be having contributions both to the AP term as well as the B term. So the AP term will get incremented by 2k delta x, 2k delta pi by delta x, and your B term will be integrated, will be incremented by the same term multiplied by your east boundary. Similar thing will happen for all the cells. Now when you consider cells, when you have the corner cells where you have both the east, something on the northeast, you have a north boundary as well as the east boundary. In that particular case, since these ifs will go over both the states, so you have contributions both from the east boundary as well as the north boundary adding into these equations correctly. The solution procedure is again similar, just that the only difference is previously we were having just two phases. Now instead of t of I plus 1, I am just writing as t of fe of I plus 1, fe of I. Fe will tell you what is the east phase index. So that appropriate index will be fed into this temperature field that is stored as a 1D array. So that's the only difference. And then you will calculate the error as and when the error is below the tolerance level that is specified, this will kind of converge. So maybe I'll show you some of the plots. So the first plot is the analytical solution, the one we have derived using the Fourier method that I have shown. So I've just taken 10 terms into consideration, and this is the solution you get. You can see like the boundary conditions are 0 on all the 3 sides, and on the top it is a 1. So this is what you get. So now this is the solution I get from the FEM method. So to compare the analytical solution and FEM, what do we do? Instead of seeing from the contour plots, what I have done is I've taken at the midplane, exactly at x equal to 0.5 and along the vertical line. At this midplane, I am comparing the solution from the analytical as well as the FEM method. So they are kind of agreeing well with each other. So it seems okay, pretty good, just with around 11 by 11 grid. So this is around for 11 by 11 grid. So now then the next obvious case is to solve the problem for an anisotropic medium where kx equal to 1 and ky equal to 5. This is the solution I get. So you can increase the number of points to see the convergence and all of that, which I have not done here. So that kind of pretty much ends the discussion for today. And then one more point that I would like to bring to your attention is is essentially something regarding to when you should be applying this finite volume methods. So let's just take an example of your boundary layer equations or your Glacier solution. So if you're aware, so you use finite volume method essentially when you have some conservative equations. So you have something that has to be conserved, that is essentially when you apply these equations. So the Glacier equation will be something like this, or maybe we'll keep it up in the next session. We will discuss this in the next session. I think we are well within the time, so I think we can conclude the session for now. Thank you all for joining, and we'll meet you next week.